Yeah, so thank you. I'm glad to be here. It's been a really interesting symposium so far. I'm giving this talk on behalf of the FIRE collaboration, and in particular Phil Hopkins at Caltech. He's really sorry he couldn't be here, but basically familial obligations prevented that from happening. So I'm going to talk about the small-scale crises in lambda CDM, our default cosmological model. But before I get into that, I think it's going to be helpful to talk about what FIRE is, but before I get into that, I have to talk about what galaxy formation is. So galaxy formation follows in the standard paradigm. For those of you that aren't familiar with this, we start with a very smooth background that's dominated by dark matter. So dark matter dominates total mass. Dark matter, of course, is some type of mass that only strongly interacts via gravity. We hope there are other types of interactions with the standard model, but we don't know yet. So there's no electromagnetic forces and no pressure in dark matter. It's our standard assumption here. That density field of the dark matter is initially very, very smooth with just tiny fluctuations that are seeded during inflation. And gravity causes these fluctuations to grow, starting with the smallest ones that merge together and make bigger collapsed structures, and those merge together and make even bigger ones. So this, from a physics point of view, is very easy to simulate because this is just gravity, and we know how gravity works. So when you put this into a supercomputer and you run this simulation, this is a VL2 simulation from about 12 years ago now, you get a picture that looks like this, where, like I said, you get these very small structures that are collapsing first, those merge together, and you form this hierarchical picture of structure formation, where this here would host a Milky Way sized galaxy at the end of the day. Now, there's a problem here, though, when you try to actually include that galaxy, which is that this is a gravity-only simulation, like I said, and we know that other physics are important for galaxy formation. And those other physics are much harder to include in the simulation. So to give you an idea of what some of those physics are, well, a galaxy is a factory that turns gas into stars. So we need to start with some gas. So that gas, in the standard paradigm, falls into the potential well that the dark matter creates. When it falls into the center, it's going to shock heat. So then it expands to fill the dark matter halo. But then this gas can cool, but it also has angular momentum. So as it cools, it collapses back down. We get a nice disk. That disk of gas starts forming stars. But then things are even more complicated because stars do things. Stars return energy to the intergalactic medium and the interstellar medium. And so there's feedback from these stars. It could be things like supernova that could drive outflows out of the disk, maybe even all the way out of the halo. And the problem here, this is even more complex than I made it look right now, because all of this is happening on this really tiny scale in the picture of the halo. So we're dealing with these enormous dynamic ranges, much bigger than 10 to the 6 in length, and in terms of time, we're talking of orders sort of 10 to the 8 to 10 to the 9. So this is a very difficult problem. In FIRE, we're trying to tackle this problem, just to drive home how big of a scale we're talking about here. We're starting with the Hubble volume. You can zoom in and talk about the clusters that Tom was talking about earlier. The galaxies would live within those clusters. And then finally, you get down to sort of star-forming scales that, of course, feed their energy back up into the Hubble volume. So here's a movie from this actually might be one of your simulations, I'm not sure, of a reionizing universe, basically. So all of these scales couple together in really difficult ways to capture, basically. So in FIRE, we're trying to model those physics that drive galaxy formation, basically. So that means that we run simulations that have fully self-consistent cosmological collapse. We have hydrodynamics and gas cooling, of course. And then we have star formation in self-gravitating gas, cold self-gravitating dense gas, basically. But FIRE is, of course, about the feedback. So we also have energy return from the stars that are based on the results of stellar evolution studies. So we have stellar winds, we have radiative feedback, and we have supernovae. And you can see down here in the corner, this is an image or a movie of a star cluster forming. So you start with a clump of gas, you collapse and fragment down, and then those supernova go off and blow out all the remaining gas. So to give you a brief overview of the types of things we're studying with FIRE, I'm certainly not expecting you to read this whole slide. I just want to drive home that we have a huge range of topics that we're interested in. Here's a word cloud of something like the 55 papers or so that have come out of Fire 2, I believe, although I might have included some Fire 1s in here. Clearly, we're interested in galaxies and stars and cosmological stuff. But there's a lot of other things that we're interested in here too, such as Lyman alpha is on here somewhere, and dark matter, and how we drive galactic winds. As for who is Fire, at this point, Fire includes 10 PIs spread across 10 different institutions. So Phil obviously is who I'm giving this talk in standing in for, but we also have people at UC San Diego, Northwestern, CETA, UC Davis now, UC Berkeley, UC Irvine, UT Austin, the Center for Computational Astrophysics at the Simons Foundation, and even ETH Zurich now. And of course, with those 10 PIs, we have avoider 35 to 45, or maybe even more students and postdocs in Fire. These are just people I was able to find pictures of. I think there are even more that I'm probably not even aware of, to be honest. I'm sorry? Yes, and Teddy is the postdoc at UC Davis. Actually, he might now be I'm not sure if they've come up with a portmanteau for professor dog. I don't know. He was a postdoc when Andrew Wetzel was a postdoc. Okay, so what I want to talk about, though, are the small-scale problems in lambda CDM, because that's what I mainly focus my research on, and, well, I'm the one giving this talk. So let me spend a few minutes introducing you to what those small-scale problems are. So if we come back to this picture of a Milky Way-size halo, redshift 0 today, then remember that we have a Milky Way at the center of our halo, very small in the scale of this picture, but you can also see that we have a ton of collapsed structures, small things that we call subhalos, living around our main galaxy. So the question is, what lives in these? Well, in the standard paradigm, we think that dwarf galaxies live in those subhalos. So dwarf galaxies range from things that are a few by 10 to the 9 in stars, like the LMC, all the way down to things that are a few thousand stars, like Pictoris 1 or Ariadnes 2. So there's a huge range here. But these things are really small, and they're really difficult to study anywhere other than the Milky Way and the local group as a whole. So if we return to this picture, then you see that there are thousands of these subhalos around VL2, right? But that image I showed you that has 9 dwarf galaxies, that's actually an appreciable fraction of the number of dwarf galaxies that we know of total. There are about 30 to 50 dwarf galaxies known around the Milky Way, right? So while theory predicts thousands of subhalos, observations say there are tens of so-called satellite galaxies. Now this is the standard missing satellites problem that was pointed out a long time ago, and there's a very sort of easy solution to this, which is that you postulate and say, hey, maybe only the biggest dark matter subhalos were able to cool gas and form stars. Now as a corollary to that postulate, you should be able to pick out the biggest subhalos in this simulation and say, are those compatible with the known galaxies that we see around the Milky Way? And when I say compatible, what I really mean is, are the dynamical, the total masses of those galaxies consistent with observations? So are the simulations and observations consistent there? So what we're going to look at is the rotation velocity, just square root gm over r. So this is basically enclosed mass. And if we go out and we measure or constrain the rotation velocity of the observations, then we get points like this. So each point here is a constraint on the total mass within a given radius for a dwarf galaxy of the Milky Way. Then we can go into the simulations and we can plot the line, the actual mass profile or circular velocity profile of the subhalos that this postulate says should host those galaxies, right? And what we get are lines that lie above all of our data points here. So what this says is that the big clumps that we naively postulated should host the bright dwarf galaxies of the Milky Way have too much central mass to actually host those systems. And this is particularly problematic because these big clumps are the ones that we say are too big to fail to form stars. So this is a too big to fail problem, or as I'll call it, the central mass problem. Now, there's a caveat, which is that these curves are taken from gravity-only simulations that ignore physics that we know about, galaxy formation, right? They ignore physics that we know exists. So the question that I want to pose is, can known standard model physics that we just leave out of gravity-only simulations, either because they're computationally expensive or really difficult to correctly model, can those physics resolve the missing satellites and central mass problems, or do we need to invoke new physics, by which I mean new physics in the dark sector, such as self-interacting dark matter? So before you think that I'm delving into a tiny corner of parameter space here, I would argue that the questions I just posed relate to really all of the points I've highlighted here. So this is a very broad question with big implications. So how are we going to tackle small-scale problems in the fire simulations? Well, first I'm going to talk a little bit about a couple suites of simulations that we have now at high resolution, looking at Milky Way-like galaxies that are run at high enough resolution that we can actually resolve the dwarf galaxies around the host. Then I'm going to talk a little bit about some isolated dwarf galaxies that we're running at absolutely ludicrous resolution. And finally, I'll very quickly touch on the currently running triple Latte simulation. So let's start with what I'm calling ELVIS on Fire and the Latte suite. So ELVIS stands for Exploring the Local Volume in Simulations. So these are simulations like this, where we have a Milky Way analog and an Andromeda analog. We're zooming in on those two. So these span of order 10 to the 6 parsecs, while still resolving of order 1 parsec scale. So if you zoom in on the center here, then these are what these galaxies actually look like. And now the image in the back is just fading between the stars, the dark matter, and the gas. And what you can see is that there's a ton of structure in the dark matter that's not present in either the gas or the stars. So in other words, a lot of the dark matter clumps that are forming in the simulation don't host stars, don't have galaxies in them. So this is moving to resolve the missing satellites problem. Right? So if we actually quantify this statement, I'm going to do that with what I'm calling a stellar mass function. So on the x-axis, we'll have stellar mass, just the mass of a given galaxy. Now on the y-axis, I'll plot the number of galaxies brighter than that stellar mass around a given host. I'm going to look within 300 kiloparsecs just as a nice round number here. And we can start by putting the Milky Way on here, but we also have Andromeda, so I'll go ahead and put Andromeda on here too. So these are the observations, basically. Now, how do our simulations do? Well, let's start by putting the picture I just showed you on that last slide. That's Romeo and Juliet. You can see here there is no missing satellites problem in this simulation, right? We're actually predicting fewer satellites than are observed around the Andromeda. Slightly more than M31, but this discrepancy is nowhere near the sort of couple orders of magnitude discrepancy that's typically talked about with missing satellites. This is consistent with scatter, basically.
At what point do you start to get suspicious due to mass resolution?
Right, so the mass resolution of these simulations are 7,000 in the isolated, in the Latte simulations, sorry, 7,070. So that's the initial baryonic particle mass. Stars end up being, once they lose mass from stellar winds and stuff like that, star particles tend to be of order 4,000 solar masses in those runs, if I remember right. The ELVIS run, so this one here, has a resolution twice that, so 3,500 solar masses. So I feel confident that we resolve the existence of galaxies all the way down to, this is applied down to, I think, 7 by 10 to the 4. I feel confident that we resolve those galaxies, that they exist. Their masses may vary by 10 to 20%, but you know, I'm confident that they're reasonably accurate. Above about 10 to the 5 here, I'm very confident. And I would argue that not only do we have the stellar masses right, but I think we probably have most of the internal properties right.
But even on the variable factor of 2, nothing will change.
Exactly, yeah. Yeah, in fact, you probably have more freedom to play around with the masses of the observations, where you have to assume a mass to light ratio to convert from the luminosity to a stellar mass. So you can play around with a factor of 2 there too. So we have more than just Romeo and Juliet, of course. We also have a second pair that I haven't shown you that I'm calling Thelma and Louise. That also matches very well with the Milky Way stellar mass function. And then, like I said, we have this Latte suite. And that is a set of isolated Milky Way galaxies. So rather than a Milky Way and Andromeda pair, just a Milky Way alone. And again, we do a fantastic job of reproducing the stellar mass function of the Milky Way and even slightly underpredict M31, Andromeda's stellar mass function. If you're interested in that latter point, please come talk to me afterwards. But I'm running out of time, so I'm going to go quickly through the remainder of this and talk about the central mass problem. Are we actually able to capture the internal structure of those simulated dwarfs? Now, I'm arguing in a paper that's going to show up on the archive either later this week or next week that even in these Milky Way and local group simulations that we are, But for the purposes of this talk, I want to talk about the ludicrous resolution isolated dwarf galaxies. So if we focus on this, these simulations have gas particle masses of 30 solar masses. These are being run by Coral Wheeler. These are the first cosmological simulations that have been run to redshift 0, as far as I know of at least, to resolve the cooling radii of individual supernova. So with 30 solar mass gas particles, a single star particle is actually basically a single star. We then have density profiles resolved down to about 30 parsecs, which is well within the sort of range that the central mass problem talks about. And in order to get to these resolutions, what we're doing is targeting isolated dwarfs, that is, systems that are in a void nowhere near a Milky Way-like galaxy or an Andromeda galaxy. So these are isolated dwarf galaxies at just astounding resolution, I think. So what are the internal structures of these simulations? So here, I'm plotting constraints from systems in the local field. So these are dwarf galaxies. They're not satellites of the Milky Way or Andromeda, but they're relatively nearby to us within about a megaparsec. And I can go ahead and put on here the prediction from the gravity-only simulation. And okay, it can fit in Leo T, and Tucana is a weird galaxy that's way up here. But in general, the gravity-only simulation predicts that this galaxy, this halo, has too much central mass to host the vast majority of the observed dwarfs in the local group. However, when we add in baryonic feedback, stellar feedback, in a system that forms about 3 by 10 to the 6 stars, then we get this curve. And this line is now perfectly consistent with just about every one of the dwarf galaxies that we see in the local group. So how does this happen? Well, the basic gist is that we're basically forming cores. This has been talked about for probably longer than I've been alive. But the idea here is that when you have bursty star formation feedback, the supernovae are able to drive galactic winds that drag some of the dark matter with it. They add energy to the dark matter. So you go from the prediction of a gravity-only simulation, where you have an r to the -1 profile here, so an NFW cuspy profile, to effectively an r to the 0, right? However, this is a galaxy that is about 3 times 10 to the 6 in stars, and is only about 10 to the 10 total mass. We have a second one of these at the same resolution, that only forms about 10 to the 4 solar mass in stars. So this is just stochasticity in the stellar mass-halo mass relationship. We end up with a lot lower mass in this one. And as you can see, in this one, we still have a cusp. So there's not enough energy in this galaxy to form a core. So yes, we do form cores, but only if you form enough stars. And this, again, I think is consistent with the results of sort of the past 5 years or so of work on this topic. Okay, finally, in the last 2 minutes, I want to talk about triple latte. So how do we push forward? Where are we going next? So triple latte, we're looking to put 1 billion particles into a single Milky Way halo, right? So at the current state, like I said, 3,500 to 7,000 solar masses. That means about 100 million particles in the halo and 300 million in the local group in the ELVIS runs. These take 1 to 20 million CPU hours, depending on how well you're able to trim down your zoom-in region, basically. Moving forward, triple latte is running right now, currently at redshift about 2.5, running with a particle mass of about 900 solar masses. That means 1.1 billion particles in the halo, and we expect it to take about 25 million core hours. So to give a sense of the progression here, basically, this is plotting the force resolution. Oh, where's my pointer? This is plotting the force resolution, basically the linear scale that you resolve, the length scale that you resolve. This is plotting the mass resolution. And while sort of the original Fire 1 runs were down here, we're now up here in double latte and ELVIS on Fire, and triple latte is going to push us all the way up to below a parsec resolution. So what does it look like? 35 seconds, great. So this is what our Milky Way mass progenitor looks like at redshift 2.5. This is at a similar depth as you could get with HST. So let's go ahead and compare it with HST, right? And this, all right, this looks pretty good, right? But of course, this is a simulation, so we can go to a lot lower surface brightness. So if we turn this down to about 10 to the 3 solar masses per kiloparsec squared, you see all this structure pop out. You see all these tiny galaxies that are going to, most of these are probably going to collapse into the main galaxy and merge with it and form the Milky Way, while others that will end up being the satellites, the ultrafaints, etc., are going to live around and outside this region at this point. Okay, I'm out of time, so thank you.